two metals, wet dirt, no solar panels, no wind turbines, no power bill. A copper pipe and a zinc rod buried 6 inches apart in ordinary garden soil generate a measurable electric current. Not for a few hours, not until the battery dies. Continuously, for months. The voltage between them reads between 0.8 and 1.1 volts. Wire enough of them in series and you can charge a phone, power a sensor, run a light. The cost of materials, under $3. The name for this device is an earth battery. It was invented in 1841. It powered the entire British telegraph network for over a decade. It was written into US military field manuals as a reliable backup power source during both world wars. And then, somewhere between rural electrification and the rise of the modern utility grid, it disappeared from textbooks, from classrooms, from public memory. This is not free energy, this is not pseudoscience. This is galvanic electrochemistry, the same reaction inside every AA battery you have ever purchased. Except the electrolyte is not a paste sealed inside a metal casing. The electrolyte is the earth itself, and nobody sells you dirt. In 1841, a Scottish inventor named Alexander Bain was trying to solve a problem. Telegraph lines required expensive copper wire strung across hundreds of miles. The wire corroded. It snapped in storms. It was stolen for scrap. Bain discovered that if you buried 2 plates of different metals in the ground, one copper, one zinc, the soil itself completed the circuit. Current flowed. Not through wire, through earth and zinc. He called it the earth battery. He filed the first patent for it in 1841, and within a decade, telegraph operators across Britain were using his design to power their lines. This was not marginal. This was infrastructure and structure. The earth battery powered real communication networks carrying real messages across real distances. The soil did what copper wire was supposed to do for free. But Bain's invention had a problem. Not a technical problem, a business problem. The telegraph companies made money selling copper wire, maintaining lines, and charging for transmission. An earth battery eliminated the wire, it eliminated the maintenance, and it threatened to eliminate the revenue. By the 1870s, commercial telegraph companies had quietly moved away from earth batteries, not because they stopped working, because they worked too well and the wrong people were profiting from them. But the technology did not disappear entirely. It went underground, literally. In 1874, an American inventor named Erasmus Loomis filed US patent number 157,478 for an improved earth battery that used carbon and zinc plates buried at different soil depths to exploit the natural voltage gradient in the ground. His design produced stable current for over a year without any maintenance. In 1898, a physicist named Nathan Stubblefield demonstrated a wireless telephone powered entirely by earth batteries in Murray, Kentucky. Over 1,000 people watched him transmit voice across open ground, no wires above, no wires below, using nothing but buried metal rods and the conductivity of wet soil. The New York Times covered it. Scientific American mentioned it. And then Stubblefield's funding dried up. His demonstration stopped. He died alone in a farmhouse in 1928, and his devices were never commercially manufactured. The earth battery kept being rediscovered, and it kept being forgotten, not because of a conspiracy, because of something worse, economics. There is no recurring revenue in a device that runs on dirt. Here is what is actually happening underground. Every metal has a property called electrode potential, valued at a measurable tendency to either give up or attract electrons. Zinc has a strong tendency to give up electrons, copper has a strong tendency to attract them. Electrode potential determines which way the current will flow. When you bury both metals in wet soil, the moisture between them acts as an electrolyte, a conductive solution, serving the same role that acid plays inside a car battery or that paste plays inside a AA cell. Electrolyte in the soil completes the circuit. The zinc begins to oxidize, it loses electrons. Those electrons flow through the wire connecting the two metals from zinc to copper, and that flow of electrons is electric current. This flow is small, but it is continuous as long as the chemistry continues. Oxidation is what drives the reaction. This is not theoretical. This is the same galvanic reaction that Alessandro Volta demonstrated in 1800 when he built the first battery in human history. He stacked zinc and copper discs separated by cardboard soaked in brine, the voltaic pile. Every battery on Earth is a descendant of that design. The only difference with an Earth battery is the electrolyte. Instead of acid or salt paste sealed in a canister, the electrolyte is the water and mineral content already present in the ground. Electrolyte and soil chemistry set the voltage and current you can get. And this is where it gets interesting. An AA battery contains roughly 20 grams of zinc paste sealed inside a steel casing. When the zinc is consumed, the battery is dead. You throw it away and buy another one. An Earth battery uses a zinc rod that weighs anywhere from 100 to 500 grams. It corrodes slowly, far more slowly than the zinc in a sealed battery, because the electrolyte concentration in soil is much lower than in commercial battery acid. The zinc rod in an Earth battery can last 1 to 3 years before it needs replacing. The copper side lasts even longer. Copper does not corrode under these conditions. It acts as the cathode, the electron receiver. A copper pipe buried in soil will function for a decade or more. So the Earth battery is not free energy. The zinc is consumed, but it is consumed so slowly and costs so little to replace that the cost per kilowatt hour approaches zero over time. There is a second factor most people miss entirely: soil temperature. Earth battery voltage increases as soil moisture increases. Rain makes them stronger. Temperature also matters. The biological activity in soil, bacteria, fungi, and decomposition generates a small but measurable electrical potential on its own. This is called the telluric current. It exists naturally in the Earth's crust and has been measured by geophysicists since the 1860s. An Earth battery does not just exploit galvanic chemistry. It sits inside a naturally occurring electrical field. The telluric current supplements the galvanic reaction. In some soil conditions, particularly acidic, mineral-rich, or heavily composted soil, the combined voltage exceeds what pure galvanic chemistry alone would predict. The US Army knew this. Field Manual FM 525, Explosives and Demolitions, included instructions for constructing Earth batteries using locally available metals and wet soil. The manual specified copper and zinc as the preferred electrode pair. It specified minimum burial depth. It specified that the batteries worked best in soil that had been soaked with water mixed with salt or wood ash to increase conductivity. This was not a science experiment. This was a field-tested, battle-proven power source used by combat engineers to detonate charges, power radios, and run field communications when conventional batteries were unavailable. One copper pipe, 3/4 inch diameter, 12 inches long. Type M cost approximately $4. One zinc rod, 1/2 inch diameter, 12 inches long. Available from electroplating suppliers, roofing supply stores, or online. Cost approximately $2. Insulated copper wire, 14 gauge. A 10-foot length costs under $3. Alligator clips or wire nuts for connections. Total cost for one cell is under $10. Step 1. Choose your location. You need soil that stays consistently moist. Not waterlogged, because that drowns the reaction. But not dry sand either. Clay-rich soil, garden. Soil amended with compost, or soil near a downspout that receives regular rainwater are ideal. The metals need to be buried at least 8 inches deep. Deeper is better. The deeper they sit, the more stable the moisture level around them, and the more consistent the voltage output. Step 2. Prepare the electrodes. Sand the bottom 6 inches of both the copper pipe and the zinc rod with 120 grit sandpaper. You want bare, clean metal in contact with the soil. Any coating, lacquer, or oxide layer reduces conductivity. Step 3. Attach the wires. Strip 1 inch of insulation from each end of your copper wire. Wrap one end tightly around the top of the copper pipe. Wrap the other end tightly around the top of the zinc rod. Secure with a hose clamp or solder for a permanent connection. The connection point must stay above ground. If the wire to metal junction is buried in wet soil, it will corrode and break within weeks. Step 4. Bury the electrodes. Push the copper pipe into the ground until only 2 inches remain above the surface. Do the same with the zinc rod, 6 inches away. The distance matters. Too close and the reaction zone overlaps, and voltage drops. Too far and internal resistance increases. 6 to 12 inches is the optimal range. Step 5. Activate. Pour 1 gallon of water mixed with 2 tablespoons of table salt around the buried metals. The salt increases the ionic conductivity of the soil. Wood ash works as a substitute. It contains potassium carbonate, a natural electrolyte. One cell produces between 0.8 and 1.1 volts at roughly 5 to 20 milliamps, depending on soil conditions. That is enough to prove the concept. It is not enough to power anything useful, yet. Step 6. Scale it. Wire multiple cells in series, positive of one cell to negative of the next, and the voltages add. 8 cells produce 7 to 9 volts. 12 cells produce 10 to 13 volts. Connect a USB boost converter rated for 5 volt output to a 12 cell series string, and you have a phone charger running on dirt. For higher current applications, wire cells in parallel. This keeps the voltage the same but multiplies the available amperage. A grid of 24 cells, 12 in series and 2 parallel strings, produces approximately 10 volts at 30 to 40 milliamps, enough to trickle charge a 12-volt lead-acid battery overnight. The US Army configuration from FM 525 used 10 cells in series buried 18 inches deep in salted soil to produce enough current to power a field telephone. That same configuration, with modern boost converters and low-power LEDs, can run a garden light, a soil moisture sensor, or a security camera indefinitely. Let us be clear about what this is and what it is not. An earth battery will not power your house, it will not replace the grid, it will not run your refrigerator or your air conditioning. Anyone who tells you otherwise is lying or confused. What it will do is generate small, continuous, indefinite electricity from materials that cost less than a takeaway meal. It will power low-draw devices, sensors, lights, radios, fans for months or years without fuel, without maintenance, and without a power bill. That's exactly why you were never taught it. The modern energy grid is a subscription model. You pay monthly, you pay per kilowatt hour, you pay connection fees, delivery charges, and infrastructure surcharges. The meter never stops. An earth battery has no meter, it has no subscription, it has no company behind it extracting monthly revenue from your need for electricity. It was not banned, it was not classified, it was simply unprofitable. And unprofitable technologies do not get taught in schools funded by the industries that would be threatened by them. The same pattern repeats across every era. Bain's earth battery in 1841 replaced by commercial telegraph wire. Stubblefield's earth-powered telephone in 1898 never manufactured. The Army's field manual earth batteries never adapted for civilian use after the wars ended. Each time the technology worked. Each time it was quietly shelved. Not because it failed the science, because it failed the economics of the people selling you the alternative. The zinc will corrode. You will replace a $2 rod once a year. The copper will last a decade. The soil is free, the water falls from the sky, and the current keeps flowing. In 1841, Alexander Bain proved that Earth itself is a battery. In 1898, Nathan Stubblefield proved it could power communication. In 1942, the United States Army proved it could power field operations and combat. In 2026, you are learning about it from a YouTube video, because nobody else was going to tell you. If you want to see us scale this, build a full off-grid Earth battery array and measure exactly how much power it can produce over 6 months, subscribe and hit the bell. The next video goes deeper.